Hi, in this video I'm going to talk about mechanical waves. Okay, and mechanical waves are basically any wave that requires a medium to travel. So if the medium is not required, we don't call that mechanical wave. It's a non-mechanical wave. An example of a non-mechanical wave will be the electromagnetic waves. Light is one of them. A mechanical wave will be like sound. So in other words, if in this room here there is no air, you will not hear me. You just see my lips moving, but you won't hear anything. And the reason for that is because you rely on some medium for the sound to travel. It's just like the ocean waves. If there is no water, there is no wave. A slinky, if you give a pulse to a slinky, you need a slinky to transverse that wave. So what is the definition of a wave? Well, a wave is something that carries energy without carrying matter. What does that mean? Well, if I take a slinky, if I have a slinky like this, okay, and if I make a pulse here, so if I pull this way fast, I'm going to see this, right? But I'm going to see this pulse traveling down to the other end. But these coils here, they just move up and down. They never get to the other side. So we call that a wave. The energy travels, but the matter doesn't follow. So also you can take a bunch of coils, okay, and just bunch them up and just release them. And you're going to see like this compression traveling down to the other end. But this coil never reaches the other end, but some energy is traveling. So we pass like a signal from one coil to the other, to the other, to the other, until we get to the end. That's pretty much what a wave is. Now, waves have some characteristics and some math that comes with them, unfortunately. But luckily, the math is easy. So a representation of a wave is like a sine wave, okay? This middle here is what we call the equilibrium position, okay? This here is what we call the amplitude, okay? I'm going to call it uppercase A. The distance between two identical points from here to here is what we call the wavelength, lambda. Okay? The time it takes to go from here to here is called the period. So the period, in other words, is the time it takes to do a cycle or to cover a wavelength. This point here is what we call the crest. This point here is what we call the trough. Okay? And I think I covered pretty much everything. Now, I can talk about the in-phase stuff. And the wavelength, by the way, I can be between here and here. Because see, this is climbing and this is also climbing. So that's a wavelength. It can be between this point and this point. Okay? So those are all wavelengths. Okay. This is a transverse wave. Okay, so a transverse wave is a wave where the medium is moving perpendicular to the direction of travel of this wave, of this energy. So it's just like taking a slinky and shaking it sideways. So the slinky goes back and forth this way, but the energy travels down. Okay, a longitudinal wave would be like taking a bunch of coils and don't shake the slinky this way, just let go. So the slinky, the coils go back and forth this way, but this energy, this compression looks like it's traveling down to the other end. We'll do some demonstrations in class so you can actually see that better. Okay? And I think that's pretty much all I have to talk about here. So let's look at some definitions. So the V is distance over time. Well, the distance here is the wavelength. And how long does it take to do that wavelength? It takes a period. Symbol for period is T. And that's in meters per second. So lambda has to be in meters and T has to be in seconds. Now, we also define, so T is the time it takes to do a cycle. We also define frequency, right? Is how many cycles you do in 1 second. So you can see that frequency is the flip of period. And the units for frequency are hertz or second negative 1 or 1 over seconds. So now if I take 1 over t and I put it in here, I should end up with wavelength times frequency. Okay? Now, we can also say, well, a wave is just a distance over time. Why can't we do that? Yeah, we can. Okay? So if you send a pulse from one end of the slinky to the other end, and you know that distance that the slinky is stretched, let's say it's 20 meters, and you know how long it takes to go from one end, for that pulse to go from one end to the other, you just do 20 divided by the time it took to get to the other end. Okay, so now let's look at how waves behave when they change medium. Well, if I have a wave going from something less dense to something more dense, and I'm going to represent the more dense with red, in red. More dense. Okay? Well, actually, before I do that, let's do this. Let's just make this a fixed end. And then I'm going to send a pulse from here. Okay? So I'm going to send a pulse. When the pulse gets to here, it comes back inverted. And the reason for that is that when this pulse gets here, it pulls upwards on this point. And according to Newton's third law, this point here is going to pull down on it. So it's going to reverse it. Okay. If I make this end loose, meaning like there's nothing fixing this, maybe like a ring on a bar. Let's say this is a bar here, and the ring can just move freely. So when this pulse gets to here, it doesn't actually pull on anything. So when it comes back the same way. Okay? So forget this less dense. So this is a fixed end, and this is a loose end. Okay? And then we'll do some other examples. What happens if you go from one medium to another? There is no fixed or loose end. So we'll see how that works in class and maybe in a lab. Okay? And I think that's pretty much waves, a quick lesson on waves. Okay, thank you.